Amplitude modulation is a real-life example of coupled oscillation being used to transfer information. In this worked example, we will not look at complicated information transfer, but we will transfer a simple song consisting of just 2 notes. The signal we want to transfer is called the modulating signal in amplitude modulation. In our case, it is given by M1 plus M2, which are the 2 notes I mentioned previously. Remember that generally a wave can be described by a cosine with frequency f, phase phi, and amplitude a. Our first note is given by the cosine of frequency f1 and amplitude a1 with 0 phase, so phi is 0. Let's take a look at how this looks like graphically. On a timescale of 20 milliseconds and with a frequency of 440 Hz, the following graph is created. Our second tone has a similar mathematical equation, but instead of A1 we have A2 and instead of F1 we have F2. Let's look at this equation graphically as well. With a frequency of 330 Hz on the same timescale of 20 milliseconds, we see that there's a little less oscillations in this same period. We can find our final modulating signal by summing the 2 notes. This gives us the following. Now, in order to simplify the system even more, we are allowed to assume that our amplitudes A1 and A2 are equal, which now will be denoted by AM. Let's take a look at how this looks graphically. On this graph, I've again plotted the individual notes M1 and M2. The final modulating signal, M of t, is given by the sum of these 2 and looks like this. Now think about for yourself what happens when either A1 or A2 becomes very small. How does this affect our final modulating signal? We want to transfer this modulating signal, and for this we need a carrier signal. In amplitude modulation, the carrier signal is given by C of t, which again is a cosine with amplitude AC and frequency Fc. In order for amplitude modulation to work properly, the frequency Fc has to be much larger than the frequencies inside of our modulating signal. Let's take a graphical look at this as well. On the same time scale of 20 milliseconds again, I have plotted a carrier signal with a frequency of 10 kHz here. If we plot our modulating signal on top of this, we can see that the difference in frequency is very big. So we should be able to use amplitude modulation with these 2 signals. The final amplitude modulated signal is given here. As you can see, our signal we want to transfer lays on top of our carrier signal. In engineering, we call this the envelope of our signal. For the next step of this worked example, you were asked to determine what mathematical relation describes this AM signal the best. It can either be given by the sum of M and C plus 1, or the product of M times C divided by the amplitude of our carrier signal, or lastly, it can be given by 1 plus M divided by the amplitude of our carrier signal times the carrier signal. Now, in order for us to determine this, let's take a closer look at the first 2.5 milliseconds of our signal, which is shown here. Let's compare this to our carrier signal. As you can see, our amplitude modulated signal, S of t, has the same 0 crossings as our carrier signal, C of t. This means that the product of C has to be involved inside our final amplitude modulated signal, otherwise it wouldn't be 0 at the points where C is 0. This allows us to cross out the first option, leaving us with either the second or the third option as the correct one for our final amplitude modulated signal. Now, in order to choose between those 2, we are going to compare our first 2.5 milliseconds of the amplitude modulated signal to our modulating signal M of t. Here I have plotted a normalized modulating signal where I've normalized it using the amplitude of our carrier signal. As you can see, this signal has 2 0 crossings, whereas the envelope of our amplitude modulated signal, ST, does not have any 0 crossings. So let's see what happens if we add a certain offset, for example +1, to this signal on the right. As you can see here, adding a +1 leaves our modulating signal completely in the positives. So if we take the product of this signal with our carrier signal, there will only be zero crossings at the point where our carrier signal has a zero crossing. This indicates that our third and final option is the correct one for our amplitude modulated signal. Let's take a look at this mathematically. So we know that our S of t is given by 1 plus mt divided by AC times the carrier signal. We can first plug in our carrier signal. This gives us the following. Just replace the carrier signal with the cosine of 2 pi fc times t. The same principle can be applied to our modulating signal. The modulating signal we found before can be plugged into to replace m of t into our signal. Now we can rearrange some terms to find that our final AM signal is given by AC times the cosine of 2 pi fct plus AM times the sum of two cosine products. Please try this mathematics out for yourself to see whether you find the same answer as well. Next, let's determine the maximum amplitude of our AM signal. Remember that the maximum value of any cosine is 1. We can thus replace our cosines in our AM signal with 1 in order to find the maximum amplitude. Rewriting this equation allows us to find that the maximum amplitude is given by AC plus 2 times AM. For the final part of this worked example, we want to determine the bandwidth. For radio signals, the bandwidth is the difference between the highest frequency and the lowest frequency transmitted. Or in other words, the difference between the highest and lowest frequency in our AM signal S of t. It describes the frequency range that is needed in order to transfer a certain amount of information, like our simple song. In order to find these maximum and minimum frequencies, we have to rewrite our AM signal in such a way that it no longer contains products of cosines but only contains sums of cosines. The first part of this is easy, since our first term already only contains one cosine. For the last two terms, we will have to employ the following rule. The product of the cosine of A times t and the cosine of B times t can be given by the following sum of cosines. The frequency of the first cosine, the angular frequency of the first cosine, is given by B minus A, and the angular frequency of our second cosine is given by B plus A. Also note that the amplitude is divided by 2 for both of these cosines. For our first term inside the square brackets, this gives us the following relation. Our second term inside the brackets can be rewritten in a similar way, giving us the following final amplitude modulated signal as a sum of cosines instead of products. Again, try out this calculation for yourself to see if you find the same answer. We found the maximum amplitude of our AM signal before. Let's do this again to see whether we did the calculations correct. Again, we will use that the maximum value of a cosine is given by 1. Filling this into our equation gives us the following. Again, we can rearrange some terms, and we should find that the maximum amplitude is given by AC plus 2 AM. This is indeed the maximum amplitude we have found before. Now that we have rewritten our AM signal, let's take a look at the frequencies that are inside. There are 5 different frequencies. Firstly, the frequency of the carrier signal. The second frequency is Fc minus F1. The third frequency is Fc plus F1. The fourth frequency is Fc minus F2. And the fifth and final frequency inside our signal is Fc plus F2. Combined with the knowledge that the first frequency is bigger than the second frequency, the first was 440 Hz and the second was 330 Hz, we can combine this to find our maximum and minimum frequency. Our minimum frequency is Fc minus F1. Our maximum frequency is given by Fc plus F1. We can plug this into our bandwidth equation to find our final bandwidth. Do note the brackets I used here. If we rewrite this equation, the two carrier frequencies cancel out and the two frequencies of the first node are added up, which gives us a final bandwidth of 2 f1 or 880 Hz. This is the amount of radio space that is needed to transfer our simple song. Let's recap what we have found in this worked example. We have shown that the amplitude modulated signal is given by the following formula. Here MT is the modulating signal, and we have taken a look at the modulating signal consisting of just 2 tones. Furthermore, CT is our carrier signal. Our carrier signal is a simple cosine with frequency Fc, which is much higher than our frequencies inside the modulating signal. If we plug the equation into the formula above and plot this, we can finally find that our AM signal of our simple song looks like this. Thank you for listening to this worked example, and good luck with your exercises.